In this video, we are going to briefly review series parallel resistances, how to find them, and we're going to derive the voltage divider rule and the current divider rule, and then we're going to do a few examples. So for series resistances, okay, so for series resistances, we said, so series resistances, so let's say we have R1, so let's say this is A, node A, R2, R3, so R4, and say we have Rn. So let's say this is B, and then you have Rn. You have N resistances in series. So the voltage here, which is Vs, and the current that is flowing. So we have voltage here, which is Vs, and the current that is flowing, and we call it Is. So we know that V is VR1, VR3, VR4, VR5, Rn. So it's, when we do KVL, it's VR1 plus VRn. So Ohm's law is R1I plus Rni. So we have R1 plus R2 plus R3 plus Rn times I. So I can call this the equivalent resistance, R equivalent. So that means Vs equal to R equivalent times the current. So essentially this is equivalent to, this is A, B, we have Vs, and then we have R equivalent, and the same current is flowing, Vs. Okay, so that means R equivalent for series, which is just R1 plus R2 plus Rn. The shorthand notation is sum I equal to 1 to n Ri. So we did derive this in the previous video. Now let's talk about the parallel. So parallel resistances. Okay, so when we have this voltage source Vs, and then let's say we still have A and B, and we have R1 and R2, Rn. Okay, so the voltage Vs will be the voltage here, Vs, Vs. So in parallel, voltage is the same. Okay, so if I call this I1, I2, IN, then the current IS, we'll do KCL, IS equal to I1 plus I2 plus I3 plus IN, and that is when we do Ohm's law, V1 over R1, V2 over R2, Vn over Rn. So Is equal to that. Okay, so but we know that V1 equal to V2 equal to V3, so it's Vs times 1 over R1 plus 1 over R2 plus 1 over Rn, right? Because V1 equal to V2 equal to V3 equal to Vn, which is equal to Vs. Okay. Okay. So then we have Vs equal to Is times 1 over R1, 1 over R2, plus 1 over Rn. So which is Is times R equivalent. So R equivalent will be 1 over R1 plus 1 over R2 plus 1 over Rn. That's what we derived from our previous video. Now, so that means this network will be equivalent to this network, and we have R equivalent connected to the voltage source between A and B, and this is Vs, and this is Vs. Now, so let's do an example. So let's say you have, so example, okay. So find the equivalent resistance seen by the voltage source. Okay, so this is the network. We have 6 ohms, so this is A, that's B, so we have 8 ohms, then we have 2 ohms, here we have 7 ohms, here we have 5 ohms, and here are 2.5 ohms. Here we have 7.5 ohms. So we have 9 ohms. Have 6 ohms. And we have 5 ohms. Now, so this is Vs. So what we wanted to do is to find the equivalent, which is Vs connected to the our equivalent. Right, this is still A and B. So to do that, right, let me see if I can copy this. Okay, so let's do solutions. So I'm gonna paste the network here. Now this and this are in series, right? Because they carry the same current. So that means we have 6. So that is 6 plus 9, which is 15 ohms. Okay. So excuse me. So we have Vs, have 6 ohms, have 2 ohms, have 8 ohms. So as you can see, we're going to work our way back from the back toward the power source. Okay, so 7 ohms, and here you have 5 ohms, and here you have 2.5 ohms, have 7.5 ohms. So then we have 5 ohms. So if you like, I can draw the 5 ohms like this. And then the 15 ohms is here. Okay. So now what do we have? So now all this will be in parallel because they share this node. Right? They share those common nodes. So 2.5 ohms, 7.5 ohms, 5 ohms, and 15 ohms are in parallel. Okay, so that means the equivalent will be, give me 1 over 2.5 plus 1 over 7.5 plus 1 over 5 plus 1 over 15. So I'm gonna put that in a calculator to see what that is equal to. So let me calculate that. 2.5 plus 1 divided by 7.5 plus 1 divided by 5 plus 1 divided by 15. And that give me 1.25. ohms. Okay, so then we have this 6 ohms, 2 ohm, we have 8 ohms. Okay, we have 7 ohms. And then if you agree with me, see that the 5 ohms is now in parallel with 1.25 ohms that we calculated, right? Because they share this node and that node, right? All this node. Okay, so I can combine this and this are in parallel. The 5 and the 1.25 are in parallel because they share these 2 common nodes. So let's calculate that. So 1 divided by 1 over 1.25, 1.25 plus 1 divided by 5. So that gives me 1. So that's 1 over 1.25 plus 1 over 5, that is 1. So then we have 6 ohms, 2 ohms, we have 8 ohms, we have 7 ohms, and we have 1 ohm. So these 2 are in series. They're in series. So that means we have 7 ohm plus 1 ohm, which is 8 ohms. So that means the network is now 6 ohm here, 2 ohms here. Then we have 8 ohms and 8 ohms in parallel. Okay, so those are in parallel. So that's 8. So 1 over 8 plus 1 over 8, which is 4 ohms. So the last one will be Vs, 6 ohms, 4 ohms, and 2 ohms. So now they are in series. Right, so those are in series now. So that's 6 ohms plus 4 ohms plus 2 ohms. This is 12 ohms. So that means we have R equivalent, which is 12 ohms. So the network is Vs and R equivalent, which is 12 ohms. Okay, now let's talk about voltage divider rule. Okay, so voltage divider rule. So let's take an example. So this is Vs, and let's say we have two resistances, R1, put R1 here, R2, okay, and the current supply is Is, have V1 and V2. So V1, so I1, I1, V2 equal to R2, I1. So then when we write KVL, this is Ohm's law. So KVL, what do we have? We have Vs equal to V1 plus V2. So have R1I plus R2I. So Vs equal to R1 plus R2I. So this implies that the current is Vs over R1 plus R2. Now, so that means V1 is Vs times R1 over R1 plus R2. Okay. I'm gonna substitute I in that equation. It's just I, not I1. Okay. Right there. So, and then V2 will be Vs. So R2. So let's use different colors so you can see. This is V1, this is R1, this is V2. So R2 divided by R1 plus R2. So that means so in general, let me use a different color. So in general, when we have n resistances connected in series, and this is a Vs. So then to find the voltage Vx, so Vx will be the source times Rx divided by R equivalent. Okay, so when you have resistances in series, to find the voltage drop across any of the resistances, you take the total voltage times that particular resistance divided by the equivalent resistance. Okay, so now let's let's do another example. So let's say you have Vs, okay, and we have this network where we have R1 here, we have R2 here, and we have something connected to a load, got our load connected in parallel with R2, and the goal is to find the voltage V0 or VL. Let's call it VL. Okay, so how do we do that? So find, the question is to find VL. Okay, so solutions. Okay, since we have a series now, a network that have some resistance in series and some in parallel, we had to rearrange them. Now we'll compute the simplify them, I should say. So then this is our load, so this is equivalent to R1. Then here is R2 times our load divided by R2 plus our load, because these two are in parallel. These two are in parallel. So it's 1 over R2 plus 1 over R load, which is R load R2 over R load plus R2. That's what I have in there. So now we could do the current division. So because these resistances are in parallel, the voltage here across the parallel is the same. So we could use find the current. So let's say that I call this R3. So when I redraw the network, we have R1 and R3. So then the voltage, right? No need to use R3. We could just calculate that and apply our voltage divider rule. So VL will be equal to VS times R1 R2 times R load divided by R2 plus R load, the whole thing divided by the total equivalent, the equivalent resistance, which is R1 plus R load times R2 divided by R load plus R2, because they're in series. So here R1 and R2 times RL divided by R2 plus RL in parallel. Okay. Oh, I mean, sorry, they're in series, right? Because they carry the same current. Apologize. Okay, so that's why we add them up, right? That's why we add. So VL is that resistance, that VL is this. We calculate VL equal to VS times R1 R2 R load divided by R2 plus R load. So V load That's R1 plus R2 R load divided by R2 plus R load. Okay, now let's talk about current divider rule. So current divider rule. So here we have parallel resistances. Okay, so let's take this example. So this is IS, then we have A here, have B here. Let's say we have R1 and R2. So let's call this current is IS, this current is I1, the current is I2. Okay, so we know that this is equivalent to, you have R equivalent here, and we have IS, which is R1 times R2 divided by R1 plus R2, because parallel. Okay, so that means the voltage here, right, the voltage here is the same voltage here. So Vs equal to Is times R equivalent, and then we know that is also I1 times R1, right, because they're in parallel. Okay, so when we equate them, Vs equal to Vs, this implies that Is R equivalent equal to I1 R1. So if I wanted to find I1 will be equal to Is times R equivalent divided by R1. Okay, so in general, when you have n resistances in parallel, so let's say we have R1, then R2, have Rx, have Rn. So if I wanted to find the current, if I'm looking for that current Ix, based off what we did there, Ix will be equal to Is times R equivalent divided by Rx. Right, that comes from what we derive here for two resistances. Okay, so the resistance that we're looking at, Ix, X. So that's the current divider rule. So when you have resistances in parallel, the equivalent, if we can find the equivalent resistance, and then we can find the current through each of the element. Okay, so now let's do an example of voltage division. Let's do an example of voltage division. Okay, so example of voltage and current division of voltage and current division. Okay, so let's say we have 8 amps, we have 36 ohms, 44 ohms, and we have 10 ohms, and here we have 40 ohms, and we have 10 ohms, then we have 30 ohms, and we have the 24 ohms resistor, 24 ohms resistor here, and what we wanted to find is the voltage across the 30 ohm, V0, and the current I0 through the 24 and the voltage across that 24 ohms. So question 1, so use current division to find I0. Okay, to use voltage division to find V0. Use voltage division to find V0. So as you can see, we have two essential nodes, this one and this one. So the resistances are, the branches are in parallel, right? So let me redraw solutions. So we have the 8 amps source, and then the 36 and the 44 are in series. Okay, so then we can find the equivalent, which is the sum 36 plus 44, which is 80. So 80 ohms. Then in parallel with 10 ohms, and in parallel with 80 ohms, right? 10 plus 30 plus 40, which is 80, and then we have 24 ohms, and then we wanted to find this current I0. So based on what we know, I0 will be 8 amps times R equivalent divided by 24. So what is R equivalent? R equivalent will be 1 over 80 over 80 plus 1 over 10 plus 1 over 80 plus 1 over 24. So when we calculate that, that will give me what? Let me calculate that. Let me calculate that plus 1 over 10 plus 1 over 24. So that's 6. That's 6 ohms. So I0 is equal to 8 times 6 over 24, which is 8 times divided by 4, which is 2 amps. So I0 is 2 amps. Okay, so that is 2 amps. Now that meant we know the voltage across this. I call it V. So I know the voltage here, V. If you like, I can call it V0. So V0 is 24 ohms times 2, which is 48 ohms. So here I have 48 volt, I'm sorry, 48 volt, here 48 volt, here 48 volt. So you have 48 volt. Oh, that's not V0, this is V, I'm sorry. So this is V. So V is the voltage across that's V, and V, that is equal to 48 volt. So 48 volt. Let's find V0. For V0 we have what do we have? We have 40 ohms. We have 40 ohms. We have 10 ohms. Then we have 30 ohms. And the voltage across the parallel is 48. The voltage from here to here is put it here, from here to here is 48 volt, but we want the voltage here, just V0. So when we use the voltage division, V0 is 48 times 30 divided by the equivalent, which is 80. Okay, so that should give me 18 volt. Okay, so in this example we were able to find the equivalent resistance, and then use that to find the current in a branch, and then use voltage division to find the voltage across the 30 ohm resistor. Please don't forget to subscribe.